Okay, let's reconvene. So last time I discussed deep neural networks, where you can extract the features from the input image, and eventually, based on the increasingly abstract features, you can perform classification after the last feature layer. And for machine learning and deep learning, there's a distinction between a training stage and inference stage. For training, you need to perform millions of iterations of forward pass plus back propagation to adjust the weights. It requires a large CPU GPU clusters and days and weeks of training time. Uh, and for inference, it involves a single forward pass from the input layer to the output layer to produce a classification result. So it can be run on a mobile device, for example. So convolutional neural networks is the most popular neural network for perception, especially for classification. It's a combination of convolutional pooling and rectification stages followed by a fully connected layer as the final classifier. So it's commonly used for detection, classification, tracking, segmentation. Uh, so we'll not go into the details of the CNN since it's covered in other courses. So, but I mentioned the basic idea of convolution. So you have a convolution operation between the convolution filter and the image. So for example, here's an image, 5 by 5. You have 3 by 3 filter, and you perform convolution of the filter with you slide the filter across the image and generate output from the convolution operation. So this operation can be used to detect features from the input image. For example, edges. So the benefit of CNN is weight sharing of convolution filters. Because one filter only has a set of edge weights, uh, and then you slide it across the image, so this number of parameters is much reduced compared to the fully connected networks. So spiking neural networks are artificial neural networks that more closely mimic natural neural networks. Neurons in the SNN do not fire at each propagation cycle as it happens with typical multi-layer perceptron networks, but rather fire only when the membrane potential and intrinsic quality of the neuron related to its membrane electric charge reaches a specific value. So when a neuron fires, it generates a signal that travels to other neurons, which in turn increase or decrease their potentials in accordance with this signal. So here's on the left, you see a biological neuron, and on the right, in the middle, you see the neuron with a few incoming connections, and input spikes trigger the change in membrane potential. As shown on the right, every input spike triggers the increase in the membrane potential, and when it reaches a given threshold, the neuron issues output spike, and then the membrane potential is decreased rapidly upon the output spike, and it comes back gradually with more input spikes. So this is a biological model of how a neuron works. So SNN is trying to mimic this behavior. So a large deep neural networks are often memory and computation intensive, even for inference tasks. Uh, so resource-constrained embedded devices may have constraints in their power and battery capacity that cannot support a large DNN inference tasks. So this particular issue is perhaps more applicable to small mobile robots such as drones than full-sized autonomous vehicles which have powerful compute engines. So the figure shows a cat trying to squeeze into a box. So that's the research issue of trying to squeeze a large deep neural network into a small embedded device. So one approach is to do a weight pruning. Is to reduce the number and or bit widths of edge weights, especially for the fully connected layers, since weights of the fully connected layers make up majority of the edge weights parameters of the entire CNN. So here's the statistics of the a number of weights in CNN, LaNet, AlexNet, Overfit, VGGNet. These are well known deep neural networks in the literature. So you can see that the number of weights in the fully connected layer is far exceeds number of weights in even though the fully connected layer is only a few, 2 or 3 layers, number of weights is very large. So that's pruning. And also another approach is offloading. So on-device execution, the computation workload may exceed the computing or energy capacity. So it's feasible for small models or for devices with power-efficient hardware accelerators. Or it can perform computational offloading to the cloud. But they will need to consider the network transmission costs. They cost the time and energy. And also you may have quality of service degradation due to network latencies and disruptions. So one solution is to make adaptive decisions based on network condition and device workload. For example, with reinforcement learning. Or you can place edge servers in close proximity to the devices, forming a multi-tier hierarchy of device edge cloud architecture. So here's one example for computational offloading. Different DNNs offer a varied compute accuracy trade-off. Mobile optimized vision DNNs such as MobileNet and ShuffleNet sacrifice accuracy to be faster and use less power compared to the more accurate mask RCNN. If you have a small robot, for example, a drone, it may not have enough computing power to run mask RCNN, so it can either choose to run MobileNet or ShuffleNet locally, or send the images to the cloud, which runs mask RCNN and sends back the result. So you can see in the lower images, if you have a compute efficient robot model running on the robot versus the compute intensive cloud model running in the cloud. So the robot model missed a lot of the objects that the cloud model detected due to the inaccuracies of the MobileNet versus mask RCNN. So the accuracy is much lower for MobileNet, but also the size is much smaller. Computation is much more efficient. So there's a trade-off between accuracy, size, and speed for DNNs running on the device versus running in the cloud. So you need to make intelligent decisions at runtime to perform offloading. So any questions on this issue? It's based on a recent publication from Stanford.
No, I'm fine.
Okay. And also you may have collaborative processing where instead of running the DNN on the device or the cloud, you can cut it up into multiple layers, and a device executes earlier layers and transmits intermediate features to the cloud, which with reduced network transmission compared to raw data. So intermediate features are much smaller than the raw data. So by transmitting the features instead of the pixels, you can reduce the transmission bandwidth by, well, at the same time, carrying out some computation on the device. So you can have early exit, where if earlier layers can produce good enough result, they can skip the cloud access. So you perform, you add a classifier layer on each intermediate step, and when you can classify with sufficient confidence, you can skip the cloud access and directly return the result. But if your classifier says, the feature looks fuzzy to me, I don't know what that is, the confidence is low, you may still need to access the cloud. So let's move on to the next section on high definition maps. So that's the, before that, the machine learning part. Any questions? Okay. So HD map, the figure shows one example HD map. So it shows the traffic lights, crosswalk, stop line, lane arrow, lane width, lane drive path, lane boundary, and so on. So it's different from navigation maps such as Google Maps, designed for human eyes. HD maps are designed for processing by computers. It has highly accurate centimeter level 3D representation of the road network. For example, cross section, layout, locations of traffic lights, signs, semantic information of certain road segments, such as speed limits. So on the right, you can see that here's high definition map for intersection with speed limit, traffic light location, lane lines, and yeah. So the benefits of HD map, one is to help reduce region of interest, ROI, for detection of traffic elements. So if you know a little bit about deep learning for object detection and object classification, so region of interest detection is very computationally intensive. You need to scan the image to look for a particular subregion that's interesting to you. So by having HD map, you can tell the computer vision algorithm that, okay, there's a traffic light at this particular XYZ coordinate. Just look there, don't look anywhere else. This considerably simplifies the task of the computer vision algorithm. It helps with AV localization based on known object positions. So you know where the landmarks are exactly to the centimeter level, so you can perform triangulation and localization very accurately. It helps with recognition of lane center line, so which is marked in the HD map. So here is a company that's well known in the HD map business. There are a lot of companies, so I just picked one that's representative. So HD Live Map is a cloud-based service composed of various tiled mapping layers that are highly accurate and continuously updated to support connected ADAS and highly automated driving solutions. Has 3 layers. The road model layers contain road topology, road centerline geometry, and road level attributes. So that's a road level road model. It's for route planning. That's high-level planning with graph search, rules of the road, enhanced sensor functionality. And higher level one layer is HD lane model. It contains lane topology, data, and lane level attributes, lane lines, lane widths, lane markings, and so on. It's for localization, route planning, and so on. So that's for the individual lanes on the road. Localization module includes various features to support localization with roadside objects, road signs, barriers, and so on. So let's watch a video to get a feeling of how this HD map works.
Here, HD Live Map is paving the way to autonomous driving with its self-healing map maintenance technology. To heal itself, the map crowdsources vehicle sensor data about real-life changes to the world and translates them into the map in near real time, providing autonomous cars with the ability to see beyond sensors to get a better understanding of the surrounding environment, so vehicles can make safer and more proactive driving decisions. Here, HD Live Map is the map made for cars by cars.
So you see that one big issue with HD maps is to keep it up to date. Obviously, out of date map can cause severe accidents. So if any lanes blocked due to construction or traffic lights are removed or added, you gotta update your map quickly. Otherwise, the automated vehicle will be confused. So what I just showed is their live map technology, where they do crowdsourcing of many vehicles on the road, and whenever something changes, they upload it, change it to the cloud, and update the HD map. So here's so other companies have similar products. So I just show this particular one as a representative example. You have to have regular continuous updates. You cannot update it, say, every 2 months. That's not reliable. That's not good enough. So here's the you can see that this is their capture vehicle, HD map capture vehicle. So it has GPS antenna, a LiDAR from Velodyne, 80 megapixel cameras, and also MU from Novatal. So this huge thing here is used for capturing HD maps. So captures the observations and aggregate these observations in the cloud and updates the map, and which eventually publishes the map to the to the vehicles. So the obvious question is, are HD maps necessary? For example, humans don't need HD maps to drive. So HD maps versus onboard sensing. So use of HD maps limits the area of operation. So whereas if you have mapless system, allow universal operation anywhere. Use of HD maps reduces the computational burden on onboard sensing. So the more that has already been mapped out, the easier it is for the onboard sensors computers to focus on the moving parts. Whereas mapless systems must figure out everything on the fly with no prior knowledge of the environment, which is obviously more challenging. A little bit of a typo, mapless. Uh, so So in general, it's generally agreed that L4 to L5 levels of automation cannot work without HD maps, at least for now. But L2 to L3 levels may work without them. So Tesla's autopilot, for example, does not rely on HD maps. But Waymo or other companies which work at L4 or above, L4 level, they do require HD maps. So, any questions on HD maps?
No.
Yes. Aren't some sort of maps like always necessary? Like only like, let's say, just for navigation, like some GPS navigation, or like reaching a destination, planning the path that the car has to do to reach a certain destination.
Yes. So I think you need if you remember on the processing pipeline part, I discussed, yeah, this pipeline. So we have a perception, planning, and control. If you have HD maps, then the perception task is much simplified. If you don't have HD maps, you can simply use Google Maps or navigation maps for the high-level mission planner. So you can plan a route from point A to point B, but you cannot do this kind of a lane level planning, low level planning ahead of the time. So you have to perform the local planning, trajectory planning as you in real time based on your vision sensors or LiDAR sensors with no help from HD maps. But with HD maps, this kind of low-level trajectory planning is much simplified.
Okay. So it's like saying the what's it called, the route map, the let's say skeleton of the HD maps. That like a sort of map like that would be always necessary. Yes, like this. Then let's say like Tesla would have such maps, and then doing all of the rest locally with local sensors on the car, without relying on more meaty layers of the map. Is it correct?
Yeah, I think to navigate on the in the city or on the highways, I think minimum some kind of Google Maps kind of a mapping service is needed. But for field robotics, where you are navigating in the wild, and just to travel along the given path without any knowledge of any map, that's also possible. You can just track the lane, track a particular set of features without mapping. That's also fine. But for driving in a city environment, I think a minimum of navigation map is needed.
Yes. Okay. Thanks.
Yeah, so HD mapping is a big business. A lot of companies are, I think, from my AV landscape, you can see a section on map and localization-based services. Yeah, so here lists a few companies, but there are a lot more. Here is a well-known company. In China, there are a few well-known companies because high-definition mapping, it concerns, it has certain implications on national security, right? You don't want a foreign company getting a high-definition map of every city of yours. So for some countries, for example, China impose severe restrictions on who can do the mapping. Only domestic companies can do mapping in China. Okay, so let's move on to the next section, hardware platforms. The figure shows a typical automotive electrical electronic architecture. They call it E architecture. Ethernet as a high bandwidth backbone network, especially Ethernet TSN, time-sensitive networking, it's posed to be the dominating standard protocol. Also, you have standard Ethernet used for diagnostics. Diagnostics is when you have electricians servicing your car, and you need to connect into the car to run diagnostics tests. Then you have FlexRay protocol for safety critical X-by-wire applications, where X is for brake, steer, drive, and so on. So that's before X-by-wire, all the steer, brake, drive actuators are connected by mechanical linkages to the user interface. So after X-by-wire, the mechanical links are broken, are removed, and everything is connected electronically. So FlexRay is used for X-by-wire connections, but in recent years, it's gradually being replaced by Ethernet. And also media-oriented systems transport most. It's for multimedia transmission. It's also it's for telematics, infotainment applications. It's also gradually being replaced by Ethernet. CAN, controller area network, is for low bandwidth network and interfacing with sensors and actuators. It is still widely used in vehicles. It's the last mile connection to the sensors and actuators. So a LAN, local interconnect network, is mainly for body electronics, for door, light, and rear view mirrors, and so on. So as you can see, the vehicle's internal network can be a very heterogeneous, very complex topology. But in recent years, there has been a trend of platform consolidation. That is on the left, you see the traditional architecture with 80 to 100 ECUs, electronic control units, connected by different bus protocols, FlexRay, Ethernet, and CAN bus. On the right, you see the more recent centralized architecture with a few, perhaps 4 high-performance ECUs with massive computing power and large number of small ECUs for interfacing with sensors and actuators. So this centralized architecture can help reduce simplify system architecture, reduce network load, and improve system reliability. Small typo here. So especially with automated driving, the auto companies are increasingly converging towards decentralized architecture with Ethernet TSN as the backbone and CAN connecting to the sensors and actuators. So here's the trunk of an experimental automated vehicle from Ford. It's taken in 2017. So you can see a problem with this vehicle, right? Where do I put my groceries? So it really takes up the entire trunk space. So the AD hardware considerations include the power consumption. So the power consumption of electronics, including the sensors and the computing hardware for AD, may be 100 times more than that of a vehicle with regular ADAS. So this drains battery and implies increased fuel consumption or reduced range for EVs. So today, EV drivers often turn off air conditioning due to range anxiety. Range anxiety is the fear of getting stranded on the road with no battery power. So will they turn off AD and drive manually for the same reason? So Waymo and Ford now focus on hybrid vehicles, that is gasoline plus battery, while Uber uses a fleet of full gasoline SUVs due to the power consumption issue. Another related issue is cooling. High power consumption implies cooling it demands high cooling power, and form factor, as you see in the last slide, it must be compact and unobtrusive. Cost is an important issue. That's monetary cost. It's important for mass deployment. Today, the cost of electronics in the experimental AV often exceeds the cost of the original vehicle that's being adapted from. So it needs to be reduced. So the most compute intensive workload in AVs is deep learning with deep neural networks. So it's mainly inference tasks, that is from input layer to output layer going once, but it may also perform training tasks in case of online learning. To address the problems in the previous slide on the power consumption, cooling, cost, and form factor. So many vendors provide SoC, system on chip, products that integrate CPU cores with specialized computational engines for deep learning. So GPU, graphics processing unit, in this space, NVIDIA is the only serious player. Other GPU vendors, such as AMD, ARM and Intel focus on computer graphics workloads instead of general purpose computing, so-called GPU. So ARM and Intel actually make GPUs, just they're integrated with their own CPUs, so they don't sell them separately. FPGA, field programmable gate arrays. These are programmable hardware. Representative companies include Xilinx and Intel Altera. ASICS, application specific integrated circuit. There has been an explosion of specialized ASICs for deep learning in recent years, with hundreds of companies and products ranging from high performance to embedded. And digital signal processors, DSPs, these are mainly used for image pre-processing before deep learning, that is. For example, products from Texas Instruments. So a CPU versus GPU. GPU has much simpler control logic than CPU, hence has more computational elements, so-called arithmetic logic units, the green blocks. Whereas CPU has a lot of the cache, DRAM, memory elements, and control logic. Therefore, GPU is ideally suited for processing highly parallel workloads. For example, matrix multiply, which is a core operation in deep learning algorithms. But it's not good for control-intensive tasks like operating systems. So here's an analogy. When you are plowing a field as a farmer, would you prefer 4 strong oxen, that is a multi-core CPU, or 1,024 chickens, which is a GPU? So in GPU, the cores are much smaller and weaker than CPU cores, but there's a massive number of them. So similar arguments exist for FPGAs, field programmable gate arrays, and ASICs, application-specific integrated circuits. So they all exploit the natural parallelism in the workload. If the workload is sequential, then they don't have good performance. So NVIDIA, the leading company in GPUs, offers a range of products ranging from the low-end Parker to the latest high-end Orin with 200 TOPS, tera operations per second. Orin was announced in December 2019. Intermediate products include PX2, Xavier, and Pegasus, with different trade-offs between performance and power consumption. So besides CPU and GPU cores, they also include NVIDIA Deep Learning Accelerator, which is an ASIC for deep learning inference. So FPGA is reprogrammable hardware. It consists of an array of configurable logic blocks, CLBs, and interconnections, which can be configured at a design time or runtime. So here shows a cartoon figure of FPGA with CLBs, DSP blocks, digital signal processing blocks, memory blocks, and I/O blocks at the periphery. So at runtime, you can rewire the connections between blocks and reprogram the blocks so that essentially it's a reprogrammable hardware, more flexible hardware. So FPGA has advantages over GPU for deep learning inference tasks. So it's for inference. It has the advantage being able to process batchless inference. So for GPU, the programming model of GPU performs computation in batches for efficient exploitation of SIMD computational model, single instruction multiple data computational model. So for example, on the lower left, you see the inputs coming in the batch of 4, and the GPU performs computation on the 4 and produces 4 results. Therefore, the first input will see a largest latency, and last input 4, will see a smallest latency. This is very suitable for training tasks with well-known algorithms such as stochastic gradient descent with mini batches for training neural networks. But it's so stochastic gradient descent, if you know deep learning, is to collect a batch of samples and update your gradients based on the batch. The batch size can be a hyperparameter that you can tune. But the particular batch-based operation is not suitable, not ideal for inference tasks. Large batch size leads to high throughput, but also a high and non-deterministic latency for each data item. Whereas smaller batch sizes lead to a low computational efficiency. So yeah, so batch operation is like a bus, right? You have to carry a full busload of passengers to maximize your throughput. But the passengers wait for the bus. So the wait time really adds to the latency, making the latency unpredictable and long for some passengers. But FPGA can perform batchless inference, where you have a low and deterministic latency for any batch size. So on the right, you see the input 1 coming and being processed, generating result 1, input 2 coming and generating result 2, and every input sample has the same latency. Whereas on the left, in the GPU, the earlier arriving input gets higher latency because of the batch operation. So that's one benefit of FPGA compared to a GPU for inference. That is, if you see one image, you want to classify this one image. You don't have a batch of other images to be input to the GPU together on a device. Well, if it's a cloud-based inference, you're sending the workload to the cloud. Then many clients may form large batches to efficiently utilize the GPU. But for device operation, FPGA is more efficient with the batchless inference. So FPGAs can be integrated into sensors. So here, the forward camera, radar, surround view cameras, and LiDAR, they all have FPGAs embedded within them to perform processing. Or it can be used as central compute engine in domain controller or AD computer. So domain controller is a large and powerful processor that controls a particular domain. For example, powertrain is one domain, and engine control is another domain, and so on. So in the particular for the LiDAR processing market, Xilinx FPGAs have 90% of the market share. That is, the LiDARs you buy, 90% of the chance it has a Xilinx FPGA embedded within it. So Intel, the main competitor of Xilinx, is pushing hard into the automotive market with their acquisition of Altera in 2015. So ASICs for deep learning are also called neural processor units or AI accelerators. Neural processing units, I think that's a more common term. So ASICs, thanks to a dedicated circuit design, may achieve up to 10x in computational efficiency and power consumption compared to CPU and GPU, and less dramatic but still significant improvement compared to FPGA. So the drawback is loss of programmability and flexibility. In industry, almost every chip vendor provides some kind of AI accelerator. Too many to list in here. In academia, AI accelerators is a dominating topic in top conferences in computer architecture, including ISCA, Micro, and HPCA. So I discussed spiking neural networks before. For SNNs, researchers have developed acceleration hardware for SNNs. They are a good match for event cameras, which since both are based on spikes. So there are a few academic research projects, but no commercial deployments. Representative projects include IBM TrueNeural's chip, shown on the right. You have a bunch of neurosynaptic core. So neurosynaptic core essentially is the circuit that performs spiking neural network operations and connections between them, forming a network on chip. And also Intel low-high chip is another ASIC for SNN. And Spinnaker from University of Manchester is a multi-core ARM system for accelerating SNNs. So I would say that SNN accelerators are still at a research stage and has not seen a commercial deployment. So I list a few commercial products that are widely used in the market. So Mobileye is a well-known company that provides the IQ series of computer vision processors. SoCs that integrate computer vision processors. So IQ series, IQ 1 to 5, targeting different levels of automation. So for example, IQ5 is targeting level 4 to 5 automation. IQ4 is targeting level 3 automation. And performance is increasing tops from 0.0044 tops to 24 tops. Power consumption is very low, actually, 10 watts for IQ5. So the GPU figure, I did not show power consumption, but I think it's in the range of kilowatts. So here's the IQ5 block diagram. They have the computer vision processors, the ASICs, and a bunch of CPUs and peripherals and sensor interfaces and so on. So their main strength is the CV processors. That's their main product. The others are integrated on the SoC. Tesla, full self-driving chip, is the autonomous driving chip designed by Tesla, introduced in early 2019 for their own cars. So it incorporates 3 quad-core Cortex clusters for a total of 12 CPUs and a GPU, 2 neural processing units, ASICs, for deep learning, and various other hardware accelerators. So that's the NPU, 2, GPU, yeah. So NPU is just another name for ASIC for deep learning inference. So here's the chip photo on the right. So, and then there are a lot of products from automotive OEMs and suppliers. These companies don't design chips, rather they offer integration solutions based on products from chip vendors like NVIDIA. So Delphi Audi have the ZFAS, this German abbreviation based on NVIDIA Tegra K1, and Mobileye IQ3. So here's my comment. They're hedging their bet on products from 2 mortal enemies because NVIDIA and Mobileye are fierce competitors for the automotive market. So ZF Pro AI is based on NVIDIA's Drive PX2, and Bosch AI car computer is based on NVIDIA's Drive AGX Xavier, and also Continental, Visteon, NXP, Renesas. They all have some kind of AD computer product. Okay, that's the end of the hardware platform section. Any questions? Okay, yes? Okay, so let's take a break and resume at 4 o'clock.